In this example, I'm going to be showing how to calculate the area of a circle with the double integral. And the first step to do is to make a quick sketch of your graph and draw your region of integration, which in this example is the circle. And the second step is you need to label the boundary of your curves. So our curve is bounded by this equation of circle, which is x squared plus y squared equals r squared. And the next step, we're going to imagine a vertical line that's intersecting this region, and it's a vertical line. And this point right here is going to be our lower limit, lower y limit. And this point here is going to be our upper limit of integration. And we're just going to rearrange this equation that's bounding our region for y. And of course here we got the negative values of the circle, so we're going to have the minus sign in our square for our square root, and we're going to choose as our upper limit this positive value, because the square root usually usually has two solutions, the positive and the minus. And in this example, we're going to use the positive as our upper limit and the minus for our lower limit. And we're just going to put in our integration values for y here in our integral, and we're going to, and our x values for our limits of integration are going to be all the values of x that include all these vertical lines. So it's going to add up all these lines here, and it's going to give us our area for the circle. And right here, this is easy to integrate because we don't have anything in our integrand, and this dy is going to become a y, and we're just going to subtract our upper and lower limits of integration, which is right here. And we have a minus and a minus here, so that becomes a positive. And these two are exactly the same, so that's just going to be a factor of 2 times this, which we can factor the 2 out in front of our integral. And we have our lower limit of integration for our x and our upper limit of integration for our x times our integral times dx. And this is the trickier part, because it's not too obvious how you should integrate this unless you know integrating techniques. So on this, we're going to have to do a change of variables, and we're going to let x equal r sine theta, and our differential is going to be dx equals r times cosine theta. And we're going to go ahead and calculate our limits of integration for our change of variables. So we see from here, we're just going to solve for theta, and that's going to equal to theta equals sine inverse of x over r. And these limits come out pretty nice. They're not, you don't get anything too ugly. So our upper limit of theta is going to be sine inverse of r over r, and that's going to equal 1, and that corresponds to the angle whose sine is equal to 1, which is pi over 2. And our lower limit of integration is going to be sine inverse of minus r over r, and that's going to be minus 1. And that corresponds to the angle whose sine is minus 1, which is pi over 2. And we're just going to plug in our differential dx. We're going to substitute this value. And of course, there's a d theta there. And right here, we're going to end up getting a r squared times sine squared theta. So we're going to factor out this r squared, and we got 1 minus sine squared. And if we remember that sine squared theta plus cosine squared theta, that is equal to 1. And we're just solving this for cosine squared theta, so we're going to have an r squared times cosine squared theta, and that's going to become an r cosine theta. And substituting our differential, we get r cosine theta d theta. So let's see what we get once we've cleaned this up a bit. So we see that we get that this equals to 2 times r squared times our integral that we change variables, and our lower limit is minus pi over 2 to pi over 2 times cosine squared theta. And if we remember our trig identity, cosine squared theta equals 1 plus cosine 2 theta over 2. So let's substitute that in. So we substitute that in, and of course this 2 in the denominator cancels this 2 out in front, and we're left to integrate this 1 plus cosine 2 theta times d theta. So let's do this, and we get r squared factored out times this integral. That's our integrand here that's being integrated. And we got our limits minus pi over 2 to pi over 2 times d theta plus our limits of integration of our integral of cosine 2 theta. And this is easy to integrate because this d theta just becomes a theta, and we just put in our limits of integration, which we do right here, and we have a minus here and a minus here, so that becomes a positive, plus 1/2 times our integral of cosine 2 theta that we integrate, which is 1/2 times sine of 2 theta. And we put in our upper and lower limits, which are these. So we get here r squared times pi over 2 plus pi over 2 is plus pi, plus 1/2 times our integral evaluated at the upper and lower limits. And this pi over 2 in this argument cancels this 2 and this 2, so that becomes pi, and the lower limit becomes minus pi. So, and we know that the sine of pi is 0 and the sine of minus pi is 0, so this doesn't contribute to our integral. So we are left with pi times r squared, which as we know is the area of a circle, which is pi times r squared. So using integration, and we came up with the area of a circle, which is pi times r squared. Thank you for watching this video, and if you enjoy my content, please subscribe. Thank you.